Here's our last test objective on practice test B. Objective 7 is distributed practice. We're going to see a series of familiar equations, familiar problems. First one is asking about a density of chlorine gas at STP. So interesting, we've been working with a density problem in this particular chapter as well, keeping in mind that that could be for any I'll just put distributed practice, objective number 7. Going back here, density problem number 1. We understand density is defined as mass over volume. Mass typically measured in grams, volume measured in liters. And the three beautiful little letters here at STP, this can be as easy as a molar mass over molar volume. If it were not at standard conditions, we'd have to use the ideal gas equation, PV equals nRT, but it is at standard conditions. So chlorine gas is a molecular compound written as Cl2. Its molar mass is 71 grams. What we can then do is put it over the molar volume unit of 22.4 liters, and it's as easy as finding the density at STP. Remember, it's these three little words that made this problem so easy. Standard, temperature, and pressure, molar mass over molar volume. So hit with me, 71 molar mass, grams, divided by 22.4 molar volume units in liters, 3.17 gram per liter of chlorine. Second problem in our stoichiometry review, whoops, that's rendering from a previous lesson. Hydrogen gas reacts with ethene, a fuel, to form ethane in a combination reaction. Hydrogen adding on to C2H4, producing C2H6. Looks like a simple combination. So let's record that balanced equation. Molecular hydrogen with C2H4 ethene, saturating that bond to create C2H6. Coefficients all work, don't they? They're all ones. So here's our balanced equation. So 1:1:1 ratio. Easy enough. Here's the screen I want. What is the limiting reagent when 50 grams of ethene react with 5.4 grams of hydrogen? And what's the maximum yield of our product, C2H4? So a good old-fashioned limiting reagent problem. 50 grams and 4.5 grams. Let's tally what we're given. 4.5 grams of the first reactant hydrogen and 50 grams of the second reactant ethene. We want to know the maximum yield of our product, assuming, of course, we have 100% efficiency. So it's two separate mass problems might be the easiest thing to do. Start with our 4.5 grams of hydrogen, and we have a target there of the product. So I'd like to get my 3 steps to stoichiometry all ready so I can see that target, mass of C2H6. And of course we'll have a second journey to take. 50 grams of the second reactant, C2H4. Again, let's get our stoichiometry parentheses ready just so we can see our target, same target, grams of our product, C2H6. So we begin filling in from divide, we ratio, we multiply, the 3 steps to stoichiometry. Step 1 requires a molar mass to convert from grams to moles. Molar mass of molecular hydrogen is 2. We have a nice 1:1 stoichiometric ratio, so 1 mole of product forms for every 1 mole of hydrogen that's used. And we'll need a molar mass of our target, C2H6, in this last step. Carbon is 12, but there's 2 of them. Hydrogen is 1, and there's 6 of those. 24 plus 6 is 30 grams. So the molecular mass is 30. You know what? That'll be the same in the last problem here. We have the same target, so I'll just go ahead and put that down twice. I know that we'll be using it. Let's see, second round of problems. We're starting with that second reactant. Its molar mass, C2H4, well, 24 and 4 more is 28 grams, the formula weight of the reactant. Again, a nice 1:1 stoichiometric ratio. 1 mole of product is produced for every 1 mole of each reactant consumed. Let's divide, let's ratio, let's multiply. I'll start with a hydrogen line first. 4.5 grams divided by the molar mass of 2 times 1 over 1, I'll just not hit, times 30. And this comes out to be 67. I'll make that neater, my bad. 67.5 grams, choice number 1. Let's start with the second line. 50 grams of the first reactant divided by 28 times 1 over 1 times 30. And here we get 53.57. Okay, so now I know I can only make as much as the smaller of my two answers. So please take the time and circle the maximum yield choice. I cannot give any credit unless you indicate what the final answer is. So one of the answers is that we have produced a maximum amount of product of 53.57 grams. Now keep in mind there was a second part to this question. I wanted you to identify the limiting reagent. The limiting reagent is the reagent or the reactant, if you prefer that vocabulary word. Limiting reagent, limiting reactant, that ingredient that gave us the maximum yield is C2H4. It didn't ask, but just to review, we would know this guy, the hydrogen, to be in excess amounts. That's going to lead us into this next part of our question that's asking how many grams of excess reagent are left over, how much is excess left over, unused, wasted at the end of the experiment. Well, I labeled the excess reagent, didn't I? So I now know my target is hydrogen. Its unit was a gram. So I'm going to just go to the gram so I can subtract like units. My 50 grams of C2H4 is my starting point. Start with the limiting reagent. Well, go to the target, which is grams of hydrogen. It is the excess reagent. What this is going to tell us is how many grams of the hydrogen were used, and then we'll be able to subtract. So step 1, we have a new target. So we have, what was that, 28 grams, the molar mass of our reactant, C2H4. For every 1 mole of hydrogen, we need 1 mole of C2H4. Molar mass of hydrogen we determined above to be 2. So just filling in my divide, my ratio, my multiply. So here's where we go. Let's take our 50 grams of the limiting reagent, C2H4, divide it by 28. We ratio of 1 over 1 times the molar mass of 2. We have 3.57 grams of hydrogen. Now what's that telling us? This is how many grams were consumed, used up during the course of our reaction. It's not how many were wasted. We have one more step. Notice how we started with 4.5 grams. I'd like to know how many grams of hydrogen were left over in excess amounts. So I just have to subtract 4.5 minus 3.57 and about 0.93, I'll say 0.93 grams of hydrogen were in leftover excess amounts. And this is our answer to part C. So first problem, we had a review of some STP, molar mass over molar volume, calculating a density. Second problem looks like a good old-fashioned limiting reagent problem, finding out grams of excess reagent. Let's take a look at the third problem. I believe this one is going to review some some thermochemistry. There it is, thermo. When calcium metal reacts with hydrochloric acid, it generates, releasing, giving off, letting go of heat, exothermic. 100 kilojoules of heat energy is released. Let's write the balanced thermochemical equation. Alrighty. So what that will ask us to do is to turn those words into a balanced thermochemical. Calcium metal, we can put our state of matter adjective, with hydrochloric acid, hydro root word ic, hydrochloric. Acids are always aqueous. Do you see that pattern of chemical change? We have an element plus a compound. Calcium and hydrogen are going to be switching places. Pattern of change is called a single replacement, a single displacement, a single exchange. Lots of correct words there to represent the pattern. Molecular hydrogen now forms, and calcium will hook to chloride. Remember to consider charge, CaCl2. Single displacement, 2 H's, 2 Cl's, so I'll double my HCl. Now here, so far, we have what's called a balanced equation. This clearly wanted a thermochemical equation, so to emphasize, I'm going to switch color. I'm going to put this in red. The red must be there. It's asking about the delta H of the reaction. Exothermic to the tune of 100 kilojoules. My chemical equation turns into a thermochemical equation when I add the enthalpy of reaction. Enthalpy, heat of reaction. Exo happens to be negative. It's releasing heat. To turn that into an enthalpy diagram, which is what, oops, that's our YouTube video. Here's our enthalpy diagram. This is where we learn to simply separate the reactants and products on an XY graph. So I typically label heat content, separating the reactants and products. This is typically in a kilojoule. Alrighty, so if it's releasing heat, the reactants indeed contain more heat, and it's letting that go as it forms the products. And label this as well. Delta H difference between reactants and products is 100 kilojoules. Heat releasing reactants, when they form products, are now at a lower state. How many grams of calcium must react to liberate? Another just word for generate, liberate. I get my thesaurus going. 1,500 kJs of heat energy. Releasing heat. How many grams? Releasing heat is our given. Grams is what we want. So liberating negative 1,500 kilojoules of heat are being given off. We want to know how many grams of calcium must be present. Now keep in mind, just from our balanced equation, so we kind of get an idea. This is what we want to know. This is our given quantity. Given, this is what we want. So this is just the ratio. So in the heart of our problem, we've invited kilojoules in. We know from the balanced equation that 1 mole of calcium liberates, generates, releases 100 kilojoules of heat, straight from the balanced equation. kJs cancel and we're at the mole. We use molar mass of calcium to convert out to a gram. So again, emphasizing this was our given. So kJs canceled. Notice they're both negative. It would make no sense to have negative mass here using molar mass at the end. So negative 1,500 divided by negative 100 times 40. And we have 600 grams of calcium. 600 grams of calcium would be required to generate 1,500 kilojoules of heat. This is our ratio of what we started with, and here's what we wanted. Alrighty. So when we have a perfect paper, give yourself an A+.